Okay.
Okay.
So can you see my screen okay, everybody? Just let me know if you can't see it. Either let me know or send me a chat message. And I was not successful getting my webcam to work. For some reason, it does not seem to work here. I'll try it again shortly, but we'll just go with the screen for now to get started. And I do have a separate camera that I can show you, just so you can see the hardware that we're using.
Yes.
Let me move this. Put this upside down here. So this board here is the Launchpad board that you probably have over at the school there. This is the Texas Instrument F28069M Launchpad.
Yes, we do have the same units.
Okay, great.
We have another student just joining us, so if you don't mind, that he's settling down, so he's good.
Okay, well, we'll just wait a second to get started. Were you able to get the software installed on the computers there?
It's okay. You may begin, Rick. Thank you.
Okay. Was it possible for you to get the software installed on the computers so you have Solid Thinking Embed and the Code Composer Studio installed?
For me, I only have the 18-day, but Joe here has the full version installed, and
okay,
it's a 1-year version. So one machine has one full install.
Okay.
And the rest are 18 days. They didn't get a chance to update.
I see. Okay. So you have Solid Thinking Embed installed, but I'm not sure that you have Code Composer Studio, which is the Texas Instrument compiler that was also part of the installation that had to be installed.
Yeah. We believe we have. So,
okay. Alrighty. Well, what I'm going to do today is go through a whole series of examples and introduce those of you that are unfamiliar with Solid Thinking Embed to the application itself. So I'll just keep going. If you have questions, just interrupt me, please. But I'll stop every now and then and ask if you do have questions.
Okay.
What I'd like to cover today is most of everything on the left column here. So I've got probably about 50 slides. Most of those are examples that we'll go through in some detail so you can understand them. I'm going to go through a little bit of introduction on just how to use the code itself. I'll just mention the software installation. Since you've done it already, there's no reason to spend time on it. Then we'll move right into controlling features of the 69M board from Solid Thinking Embed, and move right to data collection after that, and then we'll talk about PWMs and CPU utilization. So these are all basic tools that you'll find useful when you're evaluating embedded applications using this approach. So as I mentioned, there's two things that you absolutely need in order to be able to run this code on one of these launch pads. You need the Code Composer Studio. I said version 6 or higher. I think the most recent version is 7.1. So if you just go to this website, it does take a little bit of time, but you can download it. And secondly, you don't need the Uniflash unless you intend to be running out of flash, which for us now we're not going to do. Then you need obviously the Solid Thinking Embed license, which sounds like everyone has at least 18 days of it. So I'll first start off and just introduce the application itself for those of you that are not familiar with it. It's a standard Windows type application. I'm going to launch it in a second, but there's basically the features are across the top. It's got a bunch of drop-down menus. The ones that you'll be using primarily are going to be the Edit menu, which is going to allow you to manipulate and create block diagrams or state charts. The System menu, which is going to allow you to configure the target for its update time and frequency of operation, plots, auto restarts, things like that. The Blocks menu provides all the information you need to create functionality. And then over here on the right, I didn't circle these, but the Embedded and Tools menu are the other key items here. The Embedded menu contains information for specific microprocessors, one of which will be this 69M board. And the Tools menu has in the automatic code generation features that you will need to generate code from your block diagram, download it, and run it on the 69M board. So let me launch the application first so you can get an idea what it looks like. So this is Solid Thinking Embed. What I'm looking at here is version 2017.2. I believe that you probably have 2017.1 is what you were given to load. They're fundamentally the same. There's just been some obvious improvements to it, bug fixes, things like that. So this was the menu that I spoke of across the top here that's got the various drop-downs in it. And you can see if I just scroll across, Edit has a bunch of things that you can do with the diagram. The System menu, I'll go through that in a little detail, but we're primarily looking at the system properties. Part of that drop-down menu that contains information about when you start in time, how frequently you update time, this is the update time, and the end time of the simulation or the running of the target. And then a couple features down here in the bottom that allow you to freeze the PC to run in real time, auto restart it, and auto restart retaining any memory states that might be present in the model that you've created. Over here on the right side, under the Embedded menu, these are the various targets that we currently support. And this list is always increasing, but just point out that we do support now the Arduino. So there's a whole package for the Arduino in here, as well as the Raspberry Pi we're currently working on. This ARM Linux interface for the Raspberry Pi is not fully functional yet, but it should be within a matter of weeks. The Cortex M3 is a dual-core processor. This is an ARM core with a F28 floating point unit on it. So this is used primarily to do control flow on the M3 side and actual control manipulation, if you will, on the F28 side. The Delfino, F280X, Piccolo are all types of TI, families of TI processors, along with the MSP430. Generic MCU allows you to create code for any MCU, meaning that the code is created as just a C function that can be called by a timing loop. And we also support the, let me see, I'm not seeing it on here, but we support DLLs as well. So you can create code for a DLL and run it on the PC in parallel with your model. So this little diagram that I have here is pretty straightforward. I've got a ramp signal going into a plot, and I'm going to hit the go button here, and you're just going to see it plot the ramp signal in time. And I've set this simulation up so that it begins at time equals 3, which is kind of abnormal, and goes to time equals 10. That's what you're seeing here. And it's doing it in increments of 1 second. Had I change this to 0 and rerun it, we'd see it start from 0 and go to 10. So not very exciting, but just to show you it's a time-based code. Everything works primarily as a function of time as the independent variable. So there's three features in the simulation setup that are important. One is run in real time, the second is auto restart, and the third is retained state. When you run in real time, what it does is adjust the PC so it will actually execute whatever you see here as best it can in real clock time. So in order to do that, all I do is select run in real time. And what this will do is it will try to run from 0 to 20 seconds in real time this diagram that I have in front of me. So if I run it, and if you were timing this, we'd actually have elapsed 5 seconds now, 10 seconds, and so on. So it's a very convenient way to run diagrams. Oftentimes what you'll find is you can't tolerate running in real time. It's either way too fast or way too slow. So we provide a method for scaling it by a factor. So what I can do here is run it in real time, but I can scale it by a factor of, let's just say 10, which means it would run 10 times faster than real time, exactly. So I'll hit OK, and that means this 20 seconds should run in 2 seconds. And if I were to time that, which I think I can do, let me, there's a way that you can keep track of the actual elapsed time here. If I look at this real time on the bottom, actually click to 1, but this is the actual measured time this is taking. I think it was about 2 seconds. And then we can work in the other direction as well. If you had something that was running in milliseconds, but you wanted to slow it down, you could make this a fraction of real time. So in this case, instead of running in 20 seconds, since I set it to 0.1, it would be running in 200 seconds, which is going to be unbearably slow for us to watch here. So I'll just turn that off. Auto restart is another convenient feature in this application. Again, it's available on the same screen. That's the Simulate Properties screen. And the auto restart is here. So auto restart is typically used to run multiple runs if you're trying to run possibly a sensitivity analysis or a Monte Carlo analysis of a particular simulation of a problem where you want to have a bunch of variables that you want to adjust over an envelope. The method of adjustment is something called the run count. Anything with $1 on it. Well, first of all, this is a variable, meaning it's a wireless connection. A variable, in this case, is producing data from the solid thinking embed environment. The dollar variable is a class of special variables. I think there's 8 of these that exist in any model in embed. And they just produce information about the simulation. First pass is the first pass flag. That means the first time through the model. This generates a Boolean flag. His code gem we'll talk about later. Last pass is similar to first pass, except it flags the last pass of a simulation. Random seed just has to do with identifying the seed used for the random number generators if you find yourself using those. End time, start time, and step time are these parameters that I showed you under the properties menu right here, these 3 parameters, start, time, step, and end. So you can get those read out to you and you can actually use them for something. And then finally the run count. So the run count is a dynamically changing variable that increments monotonically upward every time a new run begins. So if you set auto restart on, which I've done, what we'll see is the run count variable. I'm going to run this for a second. What you want to be looking at here is this display box, and you'll see this number tick up 1, 2, 3, 4, 5. And what I've done here is I've stopped the simulation when run count exceeds 10. So we'll run this, and I'm deliberately running it slowly, but you're seeing run count increment and the simulation restarting each time. And I'm plotting a sine wave out, and all I've done is just bias the sine wave by the value of run count, which is why you see this thing just increasing in amplitude upward. And we got to 11, it exceeded 10, so the simulation stopped. So pretty easy to run multiple runs in this language. And retain state again allows you to retain the state of memory variables. So what I've done here is I've taken a value of 1, and I've integrated it. So what I'm going to get is a ramp out of that. So during one run, in this case in 15 seconds, this thing will increment up to a value of 15. Mm-hmm. And then what I've done is I've selected retain state so that when I begin the next run, the integrator will maintain its accumulated value and then begin reintegrating from that value for the next run. So we'll find it integrating upward, and then we'll to a value of 15. Then it will maintain that value and then integrate upward to a value of 30, depending on how many times I'm running. Now I'm running 5 times, so we should see 5 of these kind of staggered increasing ramp functions. Okay, so that's exactly what's happening here. If I just blow this up and read the coordinates out right here, that it's taken the final value here, and then on the next run it has reinitialized the integrator to the final value of 15, reintegrates back up to this value here, which is 30, and then reintegrates up and continues doing that. Now, as far as simulation control, I've already shown you this, so you've already kind of inherently seen it. It's very easy to control any of these simulations. There's 3 ways of doing it. Right up here in the toolbar is this little go, pause, single step, and continue selection of blocks. So I'm normally hitting go, which you could shortcut to be an F5 key, if you see that. You could also use this control panel, which is available under view, to hit go, stop, continue, and step. Don't find this used very often, though. It's actually more inconvenient, I think, than just using the menu bar or F5. So we can run it. I can single step, and what we're seeing here as I continue to hit the single step is for every time iteration defined right here by the time step, this will reevaluate the graph and plot it, the graph being the plot diagram. And that's what I'm doing when I single step through it. So this is helpful if you want to debug a model and you want to understand what values are at specific points in time. And then if you get tired of doing that, you just hit continue and it'll continue running until the end time. So go. I can actually, this one I didn't tell you. Let me put this into real time so I have some ability to control it. I'll hit run, and what I'm going to do is pause it now. So I've actually paused the simulation, and I can do things to it. I can edit it. For example, I could put a gain in at this point, and then I could continue running it if I wanted after I modify the gain. Oh, it didn't. Sorry, it didn't take the actual value of the gain when I did that dynamically. Gain is a different block. You can do this using a multiply. So let me show this to you just so you can see it. So if we have a constant, so I'll run this. Let's pause it, change the gain to 2, and then rerun it. So I can actually change this as it's running dynamically with the pause and continue statements. So helpful when you're debugging, very flexible. Integrators, pretty much all the standard integrators are available in the application. Under System Properties, under the tab called Integration Method, it lists out all of the integrators. So the first 4 here are fixed step integrators, the Euler, trapezoidal, and 2-run katas. Then there's the variable order integrators that follow it. And there's finally down here at the bottom, this is a stiff integrator, which is seldom used. When you're dealing with embedded applications, for the most part, you're going to be using the Euler integrator pretty much universally. So don't need to be too concerned about these unless you have a concern about the accuracy of your simulated model relative to the update time that you're using. This example that I have here kind of shows you what different integration methods can produce. I have a numerical integration up here on the top, so I've taken a sine wave and double integrated it. And if you look way down here in the bottom right corner, this little information at the bottom of the screen, the last thing tucked over here in the corner says RK4. That's the integration method being used. Mm-hmm. Well, this thing next to it, this T, is the final time. This is the step time that we're using, a 0.1 second. And the range that we have is 0 to 15. This is the number of blocks in the diagram. So what we can do is I can experiment with the accuracy of the numerical integration, because I have the numerical integration here in the first line, and I've analytically just integrated it out by hand, and I've programmed it into the second line. So what I'll do is let me modify the integrator to an Euler, and we'll run that. So what we'll see is the red line will be the numerical, and the blue line will be the analytical solution. And what you're seeing now, this difference, this diverging error between them, is the result of numerical error in my integrator. So I can reduce that by decreasing the step size. Right now, as you see, I have it set to 0.1. I can decrease that, and that'll decrease this value. Or I can just move to a different integrator. But like I said, in an embedded system, you're mostly going to be dealing with Euler, and you will be dealing with pretty small update times. So this error will be acceptable pretty much in the design that you're using. So we need to talk a little bit about variables now in this application. There's a notion of wired variables, and there's a notion of wireless variables. So far what I've done in these models is I've been using, this is a constant value. I got it from one of these down here. This is a signal producer. So a signal producer is just a block that produces a signal, and I'm using the constant for it. And I've assigned it a value of 1.7. This right here is a variable, and this is available under the second category, annotation, variable. And within the variables are these dollar variables that I mentioned to you, these $8 variables.
Wireless.
In addition to any variable that you define. So you can create any variable that you want to, provided it doesn't begin with a dollar, because those are reserved variables. And there's a convention for scoping how the variable is interpreted in your diagram model. So first of all, in any model, there's a notion of hierarchy. So right now we're at the top level. Let me bring over this this tree, and you can see it a little bit better. We're looking down here at this model. So here I'm at the top level, right here. If I move into compound block A, I'm down one level. So I'm up a level, down a level. Now I can go into compound block A and again move down another level. So I'm actually at a second level in the diagram now. So in your mind, what you're picturing is this vertical hierarchy defined as levels. And with that in mind, scoping becomes easier to understand. There's three different ways of scoping variables. The first one is called diagram scope, and that's the simplest. That means the variable is available to every level of your diagram. And you simply just type in a variable name. It doesn't matter what it is. It just can't begin with a $, and it cannot begin with a colon. Anything else is a legal global variable name. If, on the other hand, if you want to restrict the scope of the variable to only the screen that you're looking at, that's called a level scope variable. And in order to make a level scope variable, you precede the name of the variable with a colon. And then there is the third category, which is called a definition scope, which is a variable that has definition at the screen it's defined at and all lower levels. So that's very handy if you're defining functions that you intend to duplicate and use separately, and you do not want interfering variables between them. So you would use a definition scope variable for that. And we'll see examples of this shortly to make it clear. I know it's a little difficult to comprehend the scoping all at one time. But what I'll do is introduce it as we need it. Now, we talked about the built-in variables. Let me get these. So here's an example of what they are. So the built-in variable, I'm plotting out first pass and last pass. And what I'm doing here is I'm running this model from time 0 to time 10, increments of 0.01 seconds. And I'm going to run it in real time, and I have auto restart on. So when I run this, we should see a pulse right at time 0 for the first pass and a pulse right at time 10 for the last pass. Then down here, what we'll see is the value that we're using for the end time, the start time, and the step time. And then down here at the bottom, we'll see the run count variable. In this case, since I have auto restart on, run count will increase, in this case up to 6 and then stop. So here I've run it, and what I want to do is I'm going to just open this plot up so you can see this. So what I've done here is in red I've plotted out the first pass and blue the last pass. So if I zoom in on this, what you're seeing here is the initial pulse at time 0. And we're seeing over here the final pulse, the last pulse at time 10. Here we're just seeing the information that I specified, the start, the stop, and the step. And then auto restart, like we've already seen before, is just that incrementing value of run count. Data types in this language are specified by color of arrows. So this little table here kind of identifies what colors pertain to. Let me just bring a small example up. This doesn't show all of them, but it'll show you a few. So here, this is an integer. It's in this light kind of green value, and if you dwell over the arrowhead, all I'm doing is just moving the mouse on it. It'll tell you the data type, int. Here is a matrix data type, and this is good to notice here. This bold line, as opposed to a narrow line, indicates this is a matrix or a vector as opposed to a scalar. And This is in double or float notation. This is a 3x3. It'll indicate what the dimensionality is as well. And then if I have a complex number, I can just denote it by the real, comma, imaginary part. And this will be identified as complex. And you'll find plenty of ways to use that. But now, as I mentioned, there's two big categories here that you'll find yourself using frequently: the signal producer and the signal consumer. Let's just look at the signal producers for a second so you get an idea of what's in here. So the button is very frequently used. This button just gives you the ability to turn something on or off. And there's a variety of options for how it works. It can be a pulse or it can be a level trigger. If I right button on it to bring up its properties, you can specify the number of states. It can have more than 2 states. It can cycle or be a push button. You can give it names. You can give it bitmaps, things like that, to make it more understandable. The constants I went over. We do support typed-in constants like pi and e. The slider is another very valuable signal producer. Again, these are located under signal producer here, so I've just selected a few of these from this list. Now the slider is neat because what you can do is you can create, just dynamically by sliding this signal, you can create your own input. All I'm doing is just moving the slider back and forth with the mouse now as we're running. The pulse train is very handy for triggering logic in your diagram. The pulse train is set up by 2 parameters. One is the initial time delay, and the second is the time between pulses. So what I've shown here is a regularly occurring pulse that occurs every 2 seconds. You can use the pulse train in other ways. Suppose you only wanted 1 pulse to occur at 11 seconds, let's say, in your simulation. Let me copy this plot over here and put the pulse train on it. What I would do is I would just put a time delay of 11 seconds, and I'd put an artificially large time between pulses on it. And then if I run this, what we'll see, I'm looking up here at this plot, is right at time 11, we'll get a single pulse then. So there you see it. The ramp function we've looked at. These are a whole series of handy functions that are pre-built in the language that you can use for creating other more complex signals. So there's a sawtooth signal, which has a time delay, a frequency, and an amplitude setting. There's a sine wave. Square wave is very useful. Again, this is specified with a time delay and a frequency. The triangle wave, very similar to the sawtooth, except it's symmetric. And it's this purple line. And then the step function allows you to put a delay in, followed by a discontinuity. So you can use the step to create different patterns if you want to. So let me, for example, suppose that we wanted to create a pulse pattern. Let me get a plot out here. What I'll do is I'll put let's suppose that we wanted to put a unit step value in at time equal 1 second. So I'm going to delay this by 1 and put an amplitude of 1 in. And then let's say that I wanted it to increase to 3 at time equals 2 seconds. So at 2, I would add 2 to it. And what I'm going to do is add these together now. And then let's say at time equal 10, I wanted it to go back to 0. So here I put in a time delay of 10, and I put in a value of 3, and I just subtract it from it. So what this will do now is this will create a more complex waveform, just using the shifted step signal that goes to 1 to 3. It'll stay at 3 up until time 10, and then it'll drop back down to 0. So you can be as complicated as you want here, and you can pretty much make up any type signal that you need to with these fundamental signals to start with. Signal consumers are just as important. What you'll find yourself using frequently are going to be the plot and the display. So again, these are located under the blocks signal consumer. First one here, display, is very useful. And well down the list here, the plot is also very useful. I think you'll probably find yourself using these most of the time. This is a display block. You can actually send into a display block text if you put it within double quotes. So what I've done is I've just typed in a string here in double quotes, and this, what I've typed it into, is just a constant block. And if I run this, you'll see in blue and green now, this is printing out this display. This is a constant block. So we can do things with it now. Suppose that I took the button, this on-off button, and in this language, the analogy of an if-then-else is called a merge, the merge block. So what the merge block does is it accepts a Boolean input, 1 or 0, which signifies true, which is the first input, or false, be passed to its output. So what I'm going to do is I'm going to attach a display to it, to the merge. I'm going to increase the number of digits in it. And what I'm going to do here is say, type a string in. So button is off if it's false, and button is on if it's true. And we'll run it. And now if I switch this button, you'll see that I can change it back and forth. So we can extrapolate on this, and you can create expressions, you can create information about intermediate data using this approach very easily. I won't go into that right now, but the flexibility is here to do that and display it on the screen. Compound blocks are kind of a fundamental part of solid thinking embed. So compound blocks are they're used to encapsulate diagrams or parts of your model into sub-level blocks. And they obviously save screen space, they hide unnecessary detail, and you can replicate them very easily just by doing a Control-C, Control-V, copy-paste. In a compound block, we have inputs and outputs defined as pins. So the notation we use is input pins and output pins. These always go from left to right or from right to left. They can't go vertically in a compound block, only left to right or right to left. And we count them down from the top always, so pin number 1 through N are numbered in that vertical manner. You can add and remove pins to a compound block from the menu, the top level menu, using this plus and minus with the arrow on it indicator, and I'll show you how that works in a second. So what we'll do is bring up this example. And here's a compound block that I've created. If I go inside of it, it's taking the first pin and it's capturing it into a variable. That's what this colon radius is. Now, colon radius is a local variable, so it only has definition on this screen that I'm on right here. Yeah, was there a question?
Yeah, how did you bring the compound block?
How did I create the compound block? Good question. Let's
Can you show it step by step?
We've got a little bit of an echo going on there.
Yeah.
Okay, let me do
Can you
that.
chart? Okay.
So if you want to create a compound block, let's say that you constructed this model right here. All you do is select what you want to have reside in the compound block, right button anywhere on it, and select Create Compound Block. Now here you can give it whatever name you want to. So this is my compound block. And then if I right button on it to go inside of it, we see the equation that I just created. Now, it didn't create any pins on it. So we can add those pins to it. If I go up here to the menu, you see right up here at the top these two selections, the plus and minus. I just click on the plus, bring this down and just click on the left side. I'll add some pins to it. And I'll do the same thing on the right side. I'll add a pin to it. I can add a few pins to it. If I don't like them, I can remove them with the subtract arrow. Now, all that did was add pins. It didn't do anything internally. If I go inside, you see the pins are here, but they're not connected to anything. So what I have to do is I have to copy and paste and define these variables. So that's what I'm doing. I'm copying and pasting them. And here I'm going to copy and paste this one here as the output. Now what I have inside is I have radius and height, goes through this equation, produces a volume. So now what I can do is I can put a constant on the height. Let's just say a height of 2.2. And what I'll do is I will put a plot on the volume. And I'll put a slider on the height. I think that was the height, the first one. I'm sorry, that was the radius. And the height I had set to 2.2. So let me dynamically change the radius with a slider. And I don't want to go negative, so I'm going to go into the slider and just limit it so it's a value of 1 to 100. And we'll let the simulation run for 15 seconds in real time. And now what I'm doing is I'm adjusting the radius, and we're getting a volume out of this thing like this. Now, everything in this compound block here is unique only to this compound block. These are local variables. So I can take and just copy this compound block if I want to. I'm just copying and pasting it here using the keyboard. And I can set it to different settings now. I can make this 2.3. And these are completely independent from one another now. Everything is independent in these compound blocks. And let's just, what I'll do is I'll just use some gains here. So we'll make this a gain of 2, and we'll make this a gain of 0.7. And I'll use these to set the top input, which is the radius input. And now if I run these, I'll just plot these additional signals here. And I adjust this, you can see all of them responding independently from one another. And all I did was create the one compound block and just duplicate it. And using the locally scoped variables inside prevents them from interfering with one another. So that's pin addition, pin removal. Now you can also, it's very helpful to be able to actually identify what these pins are so you can remember what they are instead of having to go in here and say, oh, it's radius and height. If you just double click on the arrowhead, you can type in a connector name. So this can be anything. And it's text. it's not interpreted as part of the code, so it can have spaces or special characters in it. So there's radius and height meters, and same on the output side here. Oops. A little more tricky to get to, but same principle. You just click on the arrow coming out of it and just enter in the text that you want here. And now if I copy this, it will copy with those labels on the pins, which I've just done. Did that answer your question about compound blocks? Okay. Next we'll look at another feature of compound blocks called dialog constants. What a dialog constant is it allows you to enter parameter values from the compound block level without actually having to go into the compound block. So this is pretty handy if you have a parameterized function that you really don't want anybody to be altering, but you don't mind if they enter in some different parameter values for it. So what I have here, I've created a limited integrator, which is all it is it's a block in Solid Thinking Embed under integrator. And I got the limited integrator block right here. That's what that block is. And the way this block works is it accepts this top signal, that's the value that's being integrated, and it will only integrate to an upper or lower value, and it will limit the integration there. So just so you see how the thing works, if I were to put in a 1 into this, and let's say that I limited the upper value to 3, and the lower value I'm going to limit to 0. And let me plot this out. You can see what it's going to look like. Now we're running this for 20 seconds, so putting a 1 in, it should integrate up to 20, but I'm saying only integrate up to 3. So this will go only up to 3 as you see it, and it'll stop there. So that's what the limited integrator does. And what I've done here, instead of actually entering in constant values, I'm using one special block here. This is called a dialog constant. It's under signal producer, dialog constant. And what you do in a dialog constant block is you give it a name, and you give it a default or baseline value, and you can give it a type, but it's the name and the default value that matter. So what I've done here is I've given this top one the high limit name, and I put a value of 0.2 on it as baseline. And the bottom one I've given it low limit name, and I put a value of minus 0.2 on it. So how does that work in a compound block? Here's the compound block. In order to get to the properties, and this is true with any block in Solid Thinking Embed, you want to do a Control right button. That'll bring up the properties window for whatever block it is you're looking at, regardless of whether it's a compound block or a signal producer or a signal consumer block. So here is the properties of a compound block, and there's quite a few of these, but the one that we're interested in here is this create dialog from contained dialog constants. So when I click that button, what it will do is when I right button on the compound block, it will bring up the high limit and low limit value, and it will default them to whatever I set them to in that dialog constant. Now I can set them to different values if I want to here without going into the compound block, and just hit OK. And what I'm doing down here in this plot is I'm plotting out the result of the integrator, and here you see I've limited it to 0.3 on the top side and minus 0.2 on the low side. So it is limiting it, and this is the result with the feedback loops in it of what we're seeing with that internal limiting. So a dialog constant, pretty handy for compound blocks to just make them easier and more useful for teams of people to use. I'm going to go through a couple properties here that are important for compound blocks, and that'll finish up really the basics of what you need to know about how the code operates. Enabled execution is another feature of a compound block that's very important. You can, using this feature, you can cause the compound block to either be executed or not during situations where you do or don't want it to execute. And you define the situations just with a Boolean input, which is provided to this funny little green circular input to the compound block that becomes present if you click Enabled Execution. So in this example that I'm going to show you, I'm going to incorporate a safe divide. So this is kind of a typical problem that you have where you got two numbers, you're dividing them, you're running it on some processor, but you want to make sure that you never divide by 0. So what I've done is I have this compound block here, and if I do a Control right button on it to see the properties, you'll notice that I have Enabled Execution checked. If I uncheck it, that little green circular thing goes away. If I check it, it appears. And it is that input that I wire up as a Boolean. So when that's 1, this will execute. When it's 0, this will not execute. It will just hold whatever value it had previously executed, even if it is an initial condition. So the logic here is pretty straightforward. All I'm doing is this block here that we're looking at is receiving a numerator and a denominator. They come in here into these local variables right here. And then I'm looking at the denominator. And if the denominator is not 0, this signal will go to 1. And the divide will be active, so it'll execute this code. If the denominator is equal to 0, this value will be 0. The divide will not function. Over here, the merge side, what I've done is I've then taken that information and I've used it to put in a safe value to use in the event that I have a denominator equals 0. And what I've said here is when that occurs, I want to set it equal to 0. If I look inside the divide block, it's nothing more than just a divide operation, but I'm just controlling when it occurs now with this outside logic and this enabled execution. And then I have the quotient coming out this pin, and I'm plotting it. So what I'll do is I'll run this model that you see here. We'll run it in real time for 30 seconds. And what I'm going to do is I'm going to toggle the denominator with this button here between a non-zero and a 0 value. And we'll see what the resultant divide does. It should go to 0 whenever I set the denominator to 0, and then it'll just take on the calculated value when the denominator is non-zero. So I'm running it. Denominator is set to 0, so we have a 0 value coming out. If I put the mouse over it and hold down the right button, I can see that value 0. Now I'll turn this on, and we have a value of 1.2. It's because the denominator is set to 1. Go over here and look at it. It's value 1. And I can turn it off again, and on, and so on. And over here, I'm using that string printout that I showed you in the previous example, just so I can keep track of what I'm doing when what the denominator is relative to 0. Okay, so that's enabled execution. Local time step is getting near the end of what I wanted to talk about here for compound blocks. So it's possible for a compound block to run it in its own time step, and you can do that and specify the actual time step value using this feature here in the properties screen of a compound block. You can check local time step, and you can specify how frequently you want it to run. In embedded systems, you're going to find this very helpful because we're going to have main control tasks that have to run very fast, and then we're going to have background tasks that don't have to run fast. They might just communicate information to or from the PC, and they can run slowly. So you're going to want to use this feature to identify background tasks and run those at a very large time step, and you're going to want to run the control tasks at a very small time step. And that's what essentially what we'll use this for when we get to the motor control part of this this course. Now, I always get asked about for loops. There's actually a way to use what I just showed you to code up for loops if you'd ever want to do that. So this one is kind of interesting, and it's somewhat useful. You never really want to divide on an embedded processor. So there's a way to approximate division. It's kind of elaborate. It's called the Newton-Raphson reciprocal function. And I've just copied a derivation of it out here and printed it out so you can see it. But effectively, all it is just a recursion. The current value of the division is equal to the previous value times 2 minus dx0, where dx0 is calculated right above here. And what I've done is I've taken this and I've incorporated this into a model. So you can actually see the result of, here I have D, which is defined here by this combination of step inputs. And let me show you what it looks like so you can actually see what D is. Let's see, we'll put a plot on D and just go down here and take a look at it. Okay. So D goes up to 5, and then it goes down to 2.5, and then it stays at 2.5 for 10 seconds. So that's what D is. So what I'm doing here, you can forget about this green trace for now. But what I'm doing here is I'm taking numerically just taking the inverse of it and plotting it in red. And in this block here, this is a compound block that incorporates that equation that I just showed you on the PowerPoint page. And in this, so it's an iterative equation. I've set the number of iterations to 50. So for every time step, this compound block right here is going to run from 1 to 50. It's going to run the contents of that block as if it were in a for loop. And the contents of that block is this Newton-Raphson reciprocal calculation. So as I run it, what we should see is good agreement between these two. So the fact that you're seeing the blue line only and not the red line means that the blue is plotting over the red and you're not seeing the red at all. That means this reciprocal is working very accurately. I could cut down the number of iterations and we should begin to see some error between these. Okay, there's pretty significant error here. It didn't iterate long enough to converge to a solution. So I can increase this then to maybe 22 and we should see better agreement between these. Okay, so this agreement is great. So, but that's how you would code up a for loop if you ever wanted to do that using compound blocks and the local bounds. Okay, so now you're pretty dangerous. You've learned all the basics that you really need to know to get started programming embedded processors using solid thinking embed. Let me just stop here for a second and ask if you have questions or anything I've covered so far.
Rick,
Yeah, it might be easy if you type your question. There's a really bad echo coming from you.
yeah, sure.
Okay, no render. Okay, is a simple way to find Taylor series expansion of a term. I'm not following what you're asking. You can create a Taylor series in this. There is not a function that determines the Taylor series coefficients for you, but you could write a function that would do that. Okay. The Launchpad. So you've seen the Launchpad here, and you have one there at least. So these are great little boards, pretty durable, really easy to use, and we use them with, let me find one here, for motor control. Just bear with me for a second. I want to show this to you so you can see it. Here we go. So for motor control, what we use is the 6.9M board and this inverter board, which is called a DRV8301 board. This is about a $60 board. And what it does is it just plugs onto these rows of pins. It just straddles these pins right here. It just plugs on. So you plug it on and you wire up a 12-volt power supply right here. And this is the 3-phase output up to 10 amps. This will provide to a motor. So I'm running in this example that I'll show you tomorrow. This is running a fairly good size permanent magnet motor. I think this is a 23 size motor. So it's pretty significant size-wise. It's much bigger than these smaller step motors that I have here. So, and that's all you need. You don't have to do any electronics. Everything works on this. This is an encoder input, so there's actually provisions for 2 different encoder inputs here. This particular motor has a built-in encoder, and that's what I'm using here for the encoder feedback to control position or speed. So what we're going to do is a series of experiments that are going to introduce you to the to how to program on this 6.9M board. And you'll find these helpful as soon as you start experimenting with hardware in the lab. First thing we're going to do is blink the LED on this thing, which is pretty straightforward. There's on this board, let me get the camera up here. There are oh, that's weird. You can't even see the LED when I hold it. There's 2 LEDs on it, though. I'm pointing right here. There's a blue one and a red one right in this area of the board. So what we're going to do is we're going to flash either or both of those at different frequencies. And initially what I'm going to do is pulse those with a square wave. But eventually we're going to get to the point where we can dim them using the PWM signal, one of the PWMs on this Launchpad board. So we'll get started just by blinking these using a square wave. So what we're going to do is alternately blink the red and blue LEDs, and we'll do it at 1 second intervals. And The LEDs are active low, which means that they're on when they're low and they're off when they're high. So if I give them a 1 value, they're going to turn off. If I give them a 0 value, they're going to turn on. So what we have to do in order to create a model to do that, and it's probably easiest if I just go and create a model for you or walk through the model. So this is a working model here. This will do the blinking of both LEDs. So the first thing that we need is we need this box here. And what this box is, this is located under Embedded. Now we're using the 69M, which is part of the PEKO family or the F28 family. So you want to go to the micro that you're using, and the first item in the category is always going to be the configuration block. So regardless of where you go to, each one of these has a config block in it. So we get the F28 config block out. That's what this block is here, and it's open now. So this tells you all the basics about the microcontroller. First of all, what it is, which is kind of important. You need to know that you're dealing with the F28069M. Now we support quite a few of these, so you want to make sure you get the right one. There's probably over 50 in this list here that you can select from. The speed is going to default to the standard speed of the chip itself. This is an 80 megahertz chip. And the clock source will be identified. If you have an external clock, you can use it. Typically take the default on this, which is the internal. Now you can overclock it if you want to using this multiple of crystal frequency, but we're just going to keep it at the standard clock rate. And then down here, the other thing so aside from the CPU, the other thing that's very important here is the JTAG connection, because the JTAG is this. The JTAG is what connects your PC to the launch pad. It provides, so we not only download the program on this, but we also do data exchange through that JTAG as well. So we rely on it for everything, all the communication and the programming of the embedded processor. Very important that you have the right one. So universally, we support this XDS 100 V2 USB. That's the one that you have there at the school as well. Then the rest of these, you can pretty much take the default on these for now. We don't have to worry about them. And we're going to hit OK. And what that'll do is, I already actually have one here, so we don't need to duplicate it. Just delete that. So that configures this diagram so it knows what board it's using and what JTAG it's using. So now that I've done that, I can create the block diagram that I want to download onto this target processor. I'm referring to this 69M as the target now, and I'm going to refer to our PC as the host. So what I want to do is I want to have the red LED light up and then have the blue LED light up, and I want them to alternate. So what I did was I got a square wave, and the square wave is in the blocks signal producer square wave, and I set it to 1 hertz. So that means it's going to blink at a frequency of 1 hertz. And I've complemented it with a not statement, which is available under blocks menu Boolean. And that contains all the Boolean information. And I'm using the not from that. And then I've fed this into a signal consumer, which is not under blocks any longer, but it's specific now to the embedded platform, because now I'm going out and talking to a register. Now you have to know what the red and the blue LEDs are. The red LED is register 34 or GPIO 34, and the blue is GPIO 39 on this 69M board. So in order to get these, they're available under Embedded Piccolo, which is what we're using. We're going to use GPIO, and that would be an output. So I just place one down here. And if I, yep.
Yeah, how did you get this red LED, blue LED?
Yeah.
Yes.
So the
Wait, Rick, can you hear me?
yes, I can hear you.
Yeah. We were following your. They're building the diagram as you were instructing as you're going through the instruction. So,
Yeah.
where are you at?
Yes. So GPIO 34 is defined as the red LED, and GPIO 39 is defined as the blue LED. This is in the Texas Instrument documentation. You actually have to read it to discern this, but I'm just going to tell you that's what it is. It won't change. So if you're using these GPIO values, you will light up the red and the blue. So what I'll do is this right here and this right here, these blocks I got from the Piccolo GPIO output. And what I did was I laid them out here and I went in and I configured them. So let me set this one up to be the red. So this would be channel 34. Hit OK. And that becomes 34, just like this one right here. If you go inside, even though it says GPIO 34, it's figuring out what channel and port that it has to use on this, on the launch pad. But you've set it to 34, that's what it's saying here. Same is true for the blue LED. This is set to GPIO 39, which happens to be channel 7 and port 8. I didn't enter that, I just entered GPIO 39. And the block itself transcripted that to identify the channel and the port number. Now, at this point, I've created my diagram. Before I run this on the target, I want to make sure it works. So what I'll do is I will set it to simulate for 10 seconds. I'm going to run it in real time. And all I'm going to do is plot out in red and blue what these two LEDs should be doing. And they are color coded, so red is the red and blue is the blue. So remember, this is on when it's 0 and off when it's 1. So this red one should be on while the blue one is off. And then they're going to switch. The red one will be off and the blue one will be on, and then so on. So this is occurring. There's 2 transitions per second. So we'll see this blinking at 2 transitions in 1 second, basically. So how do I get this onto the target? Now that I have it working, all I have to do is go to Tools, and I go to CodeGen. Now what CodeGen is going to do, it's going to compile this diagram, it's going to create C code, it's going to compile it, and then I'm going to download it, and I'm going to run it on the target. Now there's no way for me to communicate with it in this diagram other than to look at the LEDs and make sure they're blinking. But I don't have any data that's being sent back and forth between the host and the target in this example. So let me first hit compile. And this brings up a DOS window. Normally you don't have a problem with this unless you've made a terrible error. And you'll end up with this, this build step here that will complete successfully and then ask you to just acknowledge that it has by pressing any key. So I'm going to hit the space bar. And then what we're going to do now is this has created a what's called an out file in Texas Instrument terminology. It's the same as a hex file or an ELF file. We're going to download it. So this prepares for the download. And here's the name of the out file right here. And now I will download it. So we see it downloading. And then what we want to do is take a look at what's happening on the board. And I don't know if you can see this very well. It's very hard for me to see here with a light. But we see both LEDs alternately flashing. I don't know if you can see that at your end.
Yes, we can.
Okay. So that's fine. So that was pretty straightforward. So we can, just to make sure that we actually did something here, let me go back in and let me adjust this to be 5 Hertz. And I'll repeat the steps just so you can see how quickly you do this. All I did was change that to 5 Hertz. I'm going to go to Tools, CodeGen, Compile, press any key, download, and download. And now you may be able to see it blinking faster, but we are definitely getting the 5 Hertz out of it now on these. Okay, so that's real basic. We were able to get a very simple diagram working and running on the 6.9M that we created in Solid Thinking Embed. So let me close this, and let's move to something a little bit more challenging. But before we do that, we need to understand a few things in terms of terminology. There's, as it will turn out, things get complicated when you want to have data communication between the target and the host. What we did right now is there a question?
Yeah.
Rick, can
Yes.
we pause here because Joe tried to generate, he could compile it. He did the same block diagram and then he compiled it, but it does not produce the out file.
I can produce the text file, but not.
So you tried to do this and it did not produce the out file?
Yeah, he couldn't find any out file.
Okay.
He compiled.
What you want to do is this. So if you go onto your computer, let me bring up. Oops. So if you bring this up in your computer, Solid Thinking Embed should be installed in the root directory under, in this case, C, under a folder called STEmbed 2017. And if you go in that folder, one level in, there's something called CG folder. That's for CodeGen. And if you open that folder up and look under Date Modified, that should have in the out file that I just created. So here, the one I'm looking at right here, it's called blinkleds.out. I created at 217. That is the out file. And that's what was loaded. Now, if you don't have that, then there's a problem with the installation of Code Composer that we have to fix on the computer you're using, which we can do. Maybe not right now, but we can do that. I can fix that for you.
You can't find it,
right? Can you find this folder that I'm referring to, the Solid Thinking Embed 2017?
It's in the same folder, but there is no out. A dot out for the Blink program. He was doing very similar to exactly the same way you have instructed.
Okay. You know what we should do is, whoever is doing this, we should arrange between myself and whoever has created this out file a go-to meeting. We can do it tomorrow. And I can go through and see how you have this set up on your computer, and there's probably something not configured correctly.
Yeah. We could arrange tomorrow for them to install it. I think you might be correct in that code generator, code gen may not be properly set up.
Yeah, that's usually what it is.
All right, but we get the idea, or we get the gist of how to do it, and the download twice and so on.
Yep.
So,
now that's standalone execution, and really that's not very interesting. It's just it runs by itself. You can't really see anything, so you can't do anything. So the more interesting model to use is where we create, over here if you look on the right, we create our model that we want to run on the target using what's called a source model, and we download that onto the target, and then once the target is running, we can communicate back and forth between the host and the target over the JTAG interface using this interactive communication interface, it's called. And this becomes more complicated because when you create a source model, it'll basically just be the algorithm that you want to run on the target. When you interrogate the source algorithm, you're going to have things like plots and different gains that you might want to use, and a lot of other stuff that you wouldn't want to burden the source model with. So we create another model that's identical to the source model, but with these signal producers and signal consumers in it, called the debug model. So now we're going to expand what we just did from a standalone model to a model that uses a source and a debug model. And let me show you what I mean by that. It's easiest to show you just with an example than just talk through it. But these two models give you the ability to run in two different modes: standalone, which we just ran, or debug mode, which is this interactive communication between the host and the target, bidirectional. So you can send data, you can get data.
Rick?
Yeah.
Can you go through the steps for create?
Yeah, I didn't quite hear the whole question. What was that?
what do you want to say? Miranda would request that you walk through the steps, generate the .out file.
Walk through the steps to create the .out file? Yes. Okay. For the standalone, this.
For the blink. For the blink.
Yes. Okay. So let me start it up again. Yep, I got it for the blink. Okay. So here's the model that I created, and the steps are there's 3 steps. So we're going to go to Tools, Code Gen, Compile. You don't have to check everything should be filled out, and you take the default. The result file just is the name of the file that you have open. So I've called this blink leds.vsm. It's going to call it the same thing .c. The target, it got that information from this configuration block, so you should not have to fill that out. All this stuff is not necessary to fill out, so you don't need to do anything here except hit the compile. So we hit compile, and that's the first step. It brings up this DOS window. And then you just click any key. And then the remaining 2 steps are hit download, download. And you'll see that screen that showed the download that says download complete, and this should be running on the target at that point. So that is the procedure. It's just 3 steps. Everything is contained in that Tools Code Gen menu. No, that is for standalone operation. So, did that answer your question? Did I cover what you wanted to see? Okay, so let me proceed here to the other.
Nick.
Yes. Okay, can you go through steps?
Professor, you're
What
asking
about
some-
serial port for the blink? What about serial port? Okay, we're not talking about the serial port here, but I can generate. I can't generate out file.
All right. Let me update you on the status. Oh, you got one of them working. Blue lights and red light are flashing.
You have
Rick?
one. You have one working.
Yeah. Anna has were able to successfully generate the dot out and then download it, and now you have it's flashing the red and blue.
All right.
All right. How about you, Joe? Oh no. So, okay.
Okay, that's great.
We're good. We Kintali, are we good? Yeah.
So you have one
In that case,
installation.
we are good
Installation that's
because
installed
we got
correctly.
one working and we can repeat that. Okay.
So we probably should look at how that's installed and make sure the other ones are installed the same way. It sounds like maybe there's a problem at the installation.
Yes.
Okay, that's good news. Now,
Okay.
is that one that has the 18-day license on it, or is that the one with the year license?
Kintali, what? It's a 18-day license.
Okay. Let me talk to, I think it was Darian about the, I thought they were going to give you a semester or a year license on this for the class.
Yes. We were trying to do that. I mean, we spent last week trying to install it, but the we weren't that successful. But we went to the 18 days, and it's working at this point, and we're gonna go back to the full 1-year trial.
Okay.
After this.
Okay, so there's no problem with that. He was getting that for you, right?
Yes.
Okay.
Okay, so we are good at this point, and you can proceed with where you want to lead us to. Okay.
Okay. So what I want to talk about now is the debug mode, which gives you the ability to interactively communicate with the target using plot boxes and things like that.
Rick, could you hold on? You're asking question.
Yes.
Yeah. It's already uploaded, the out file. When you say download, it takes the out file and put it in the. Got it. Rick, you may proceed, please. Thank you.
Okay. All right. All right. So what we're going to do here is I'm going to modify the example we just did to be one that we can control the frequency dynamically of the blink of the LED. I'm going to just control the red LED. And I'm going to also put in some code that will measure the on time. And I'm going to measure the on time with this code running on the target. And I'm going to send that value back up to the host so I can plot it. So let me show you why you want to have a source and a debug model for this. I'm opening the source model right now, and the real purpose of the source model is to just create the code that's going to run on the target. So let me let me go in here so you can understand what's happening. First of all, you remember this block here. We still need this. This is just the F28 config block, and I got it from the Embed Piccolo right here, this menu. It's always the same. It'll be always the same for you. You'll have it set up the same way. If I go in it and look, it's still for the 69M, and it's still got the JTAG that we're using. What's changed is this. So now I've built a compound block, and I'm driving it with a little slider here that's going to have the blink frequency in hertz is what I have listed out here. And if I go inside the target calculations, I take the hertz signal coming in, and I'm going to process it two different ways. First of all, I'm going to create a square wave. There's a number of ways of doing this. This might be overly complex, but what I've done here is I have created, in this part of the diagram, I've just created omega t, where omega is hertz converted to radians per second. And instead of using time as just being a ramp value, you never want to do that on an embedded processor, because as time goes on, the value gets larger and larger, and numerically it becomes less and less accurate. So you always want to create time that just resets itself, which is what this little loop does here. This is an integrator. This is a unit delay, and I'm just integrating the value of the time step, and that is giving me time. But then as soon as I exceed 2 pi, I'm going to reset it and just start all over again. So all this does is create little ramp functions that go up to 2 pi and then ramp back down again. And I took the sine wave of it, so that turned it into a sine wave at that frequency. Then I used a relay, which all the relay does is it just takes the sine, basically. So if the signal is positive in value, it'll put out a 1. If it's negative in value or amplitude, it'll put out a -1. And then I've limited it to just lie between 1 and 0. So what'll happen is I'll create a square wave, which is this top output here. If I run it, you see I can adjust the hertz, and I'm looking at the top plot here, so you can see that I can adjust that on time pretty accurately with this now. So that's what the square wave output is doing. And then in the bottom part of the diagram, all I've done is I'm just measuring the on time, or the amount of time the square wave is at a 1 value. 1 value is actually the off time, but that's what I'm measuring. And the way I do it is the square wave is being fed in here, and I'm using just a timer function. Again, this is a timer. It's an integrator being fed by the time step, and then it's being reset every time the square wave goes through a rising edge. So let me plot this so you can see it. It's easier to explain it if we're looking at it.
The merge is like a multiplication.
Okay, so there's the input, and let me set it to 2 so we can actually see something here. And let's see. Let me slow the frequency way down too.
Merge.
Okay, there we go.
Okay,
so there's the square wave, and what this rising edge is doing, and the falling edge. The rising edge is identifying this rising edge value, and the falling edge this value. So you can see that. What I'll do is I'll just put I'll put a small gain on the rising edge, a gain of 1.1, and I'll plot it in blue, and I'll put another small gain on the falling edge, and I'll plot it in green. So you can see this on this plot, what these are. So the blue is the rising edge, and the green is the falling edge. So that's all these blocks are doing. And if I look inside of them, all they are is just a unit delay and a Boolean. So all I'm looking for is an increase for the rising edge or a decrease for the falling edge. So that's an edge detection, and it gives you a pulse. And what I'm doing then is using that pulse information to reset the timing loop on the rising edge. And then on the falling edge, I'm doing a sample hold on the accumulated value. So that will retain the actual on time. So if I plot that on time out, it's going to be looking pretty constant until I change the frequency. So those are the calculations that I'm doing in this. There's a number of ways of doing them. This is only one way, but this is a good way to do it on the embedded processor. It's going to be a stable way to do it using this kind of a recursive calculated time value. Then way down here at the bottom, I'm taking the square wave that I created right here, and I'm applying it just to the red LED. So that's my source model, and the only purpose of this is to create the out file. So at this point, what I want to do is let's say that I want to run this source model at 10 kilohertz. So what I would do is go into System Properties, and okay, I've got this set for 10 kilohertz already. So it's 0.1 microseconds. And what I'll do is I will identify that target calculation block only by just lassoing it with a mouse. And this is different than what you just did. All I'm going to do is lasso it, and I'm going to create code by hitting compile. Now, before I hit compile, you notice up here that something is different. I'm telling it to use the selected compound block edge pins for the data exchange. So what I want to do is I want to generate code, but I want the code to accept this pin as input, and I want it to produce these two pins as output. So this is very important. If you don't check this, you won't get data communication. So we'll hit compile, and the procedure at this point is identical, except I stop here. At this point, I have produced the out file. So I'm going to hit any key to continue and quit. And that's where the source model stops. I don't use it any longer. All I use it for is to create that out file at the update rate that I want to run it at. Now what I'm going to do is open the debug model. So let me, oops. Sorry about that. Let me open the debug model. Now the debug model is identical to the source model. So here's the target calculation block right here. I didn't change anything. But I got this funny block down here. This block here is called a target interface. It's a receptacle for the out file. So what it does a number of things. It transmits the pin information to and from the target to the host, and it runs the out file on the target. So the way you get one of these are specific again to the processor you're using. So on Piccolo, we've already looked at the config. We've looked at GPIOs. You go way down on the bottom here, it says target interface. There's one of these for every micro that we support. You want to get the target interface block right there and place it on the screen. And when you do, it will appear with the same number of inputs and outputs as the compound block that you use to create the out file. And printed in this block should be the name of the out file that you've created for it. If it isn't, if you right button on it, go into the block, it'll have the target file right here. You can hit this ellipsis and go out and make sure that you have the right one selected. It should bring you to the CodeGen folder. And in the CodeGen folder, you should just look for probably the most recent out file that you created and hit open. So things to notice here. it generated the out file at 10 kilohertz to run at 10 kilohertz. It's got one input and two outputs. And other than that, it's identical to this target calculation. So if I apply my input signal to it and I, in parallel, plot the square wave signal and the on time, what I'm going to have now on these plots is in red is going to be the model, and in blue is going to be the data from the target. So I can run this, and what we're seeing is downloading now, and I can control this. Now, this is actual recording from the target itself. So let me show you that on a camera so you can see it. Okay, let me run it again. Let's see here. Oh, you know what? This one I'm not gonna be able to show it to you. So I can move it, and you can kind of see it slowing down on here. So you can see, if you look carefully, it is running on the target. I just am unable to show both windows simultaneously. So what I've done here with these models, the debug and the source model, I've used the source model to generate the out file. The out file goes into the target interface. The debug model has got this slider in it, and it's got these plots in it that I didn't have in the source model, and I wouldn't want to put in there anyhow because they'd just be non-essential information to the source file. So we keep them separate. And the convention that's used in most of the examples is we use the same name for both the source and the debug model. The only difference is, if you look way up here in the banner, I append it always with a -D. And the only reason I do that is it makes it really easy to find it under your windows because they're grouped together. The only difference is the presence or absence of a -D before the extension. So let me actually open up the, let me open them both up so you can see how you would do this if you weren't doing this from PowerPoint. Let me go in and get the actual example here, and I'll open it. Let's see here. Just bear with me for 1 second while I find this. I don't remember what I did with it. Okay. Blink. We've controlled on time calculation. Yes. And that's not it. Yeah, I'm getting there, don't worry. There we go. Blink at. Okay, yeah, sorry about that. And also here, here, here. Blink at. Okay, this is what I wanted to show you. So now I've got both models loaded into Solid Thinking Embed. And if I go to Window, you can see them. They're listed here. This is the source model. It doesn't have a -D on it. This is the debug model with the -D on it. So now I can make changes. Let's say that I wanted to change the source model somehow. Oh, let's just say I wanted to run it faster, the source model. So let me go in and change this to 20 kilohertz. So I'll make it 0.00005 seconds, which in kilohertz is 20 kilohertz. Okay, I will generate code. Just hit compile, any key to continue. Now all I have to do is switch windows, and that out file is automatically been loaded here, and I can run it. I don't have to do anything to the debug file, and this is now running.
So, Rick, if I interpreted correctly, the blue block is simulating, and then the bottom block is actually running the code.
Correct.
On the
yes.
28. So one is simulation, one is real hardware.
That's right. Let me disconnect the simulation so we don't get so confused, and I'll just run it over again.
Yeah.
So all you're seeing here is the target running.
Target, hardware, yes.
That's what the target's doing, and I can see the LEDs responding to this.
Okay.
This is my on-time measurement here, these upper values. So you can see them increasing as I slow down the frequency and decreasing as I increase the frequency. But the key feature here is that you got both these models. You can make any changes you want to the source model, rebuild it, and then immediately move to the debug model and just run it without doing any changes on the debug model once you have it running. So it's a
when you run both of them, they should be exactly the same, but
yes,
not.
Yes, they should be identical.
But it's not really.
Well, no, they should be identical. I don't know what I did here. Let me go back to the source model, and well, they're going to be identical up to a certain point, because what happens is the JTAG interface will only transmit data at about 200 hertz. So you will lose some data in that interface, and I'm going to talk about that shortly, how to overcome that, but just plotting it out like I have it, you will lose some data.
I got it.
So here, let me regenerate code, compile, and we'll go back to here. Now, this should be the same. Huh. That's weird. Just bear with me for a second. Let me take a look at this. Something's not quite right. Oh. Okay, and let me just get the block back here. I just deleted it.
Even though you did it in the real time?
Okay, yeah, I don't know what I did. I did something, but here in the top screen, you can see they're pretty similar to one another. The difference that you're seeing here is going to be due to a number of things. One is the communication. The second one is these calculations that I did here. The omega t being compared to 2 pi, I had to limit because I was getting a condition where it went slightly above it and it would create more than one pulse on the rising edge. So that's part of the reason that you're seeing this difference in these signals. So it's pretty much in the way that I created the function is why you're seeing a difference. But other than that, at initial time, it's identical. And the error is just occurring because of numerically how I programmed it. Okay, let me continue. You guys okay? Can I keep going a little further?
Yeah, we okay, yes.
Okay, all right. So target update time. There's 3 ways that you can set it. We've already looked at one, and it's the most straightforward one. Just in the source model, go in and set the time step to whatever you want it to be. It could be 10 kilohertz, 20 kilohertz, 80 kilohertz. There's also 2 other ways of doing it. You can set it in the target interface block. If you recall, when I showed you the target interface, there was a frequency entry in it. You can change that entry, and it'll cause the embedded code to run at the frequency that you specify it. And then lastly, we can do it in the compound block, like I mentioned very early on in this presentation, when we use the local time step in a compound block. But by far the easiest way to do it is in the source model, just to set the time step, generate the code, and then run it in the debug model. Okay, what I'm going to do, I've got a couple more examples I'm going to go through for you here that'll be helpful. What I'm going to do here is just create a model of a PWM, not the real PWM on the board, but a model of it. And I'm going to use it to control the brightness of the LED. So the way I'm going to create a PWM signal is with this sawtooth signal right here, running at what's called a carrier frequency, pretty high frequency. And I'm just going to compare it with effectively a duty cycle that I'm going to specify with a slider. And what that will do, if you just think about it, what it's going to do is create a PWM signal that's going to vary the on time as a function of that duty cycle value. And what I was going to do then was take and apply that directly to the LED. And because this is going to be occurring so rapidly, the LED is going to have some inherent capacitance to it that's going to smooth this out, and it's going to respond to the average value of that PWM signal. I'm just going to basically allow it to dim and brighten. So let me bring up the model that does that. So here is my PWM model. This input here is the duty cycle fraction, and I'm comparing that to this carrier wave that I'm running at 100 hertz, which is not very fast, but that's how fast I'm running it. And I'm taking that output signal, which is, I'm calling it the PWM signal. It's going to be a square wave. And we're going to apply it to the 39, which is the blue LED. And I'm plotting it out here. So let me just disconnect this and run it so you can see what I'm doing. Okay. So you can see as I increase and decrease the PWM, this thing is doing what it's supposed to do. Okay. So what I'll do now is generate code for this, code gen, and I'm going to use selected compound blocks, hit compile, and quit. Now, in this diagram, I got done explaining the source and the debug diagram. I already have the plot block and the slider in here, so I'm not going to mess around with the debug diagram. I'm just going to add in the target interface right into this diagram and run it. So normally you don't do this, but we're going to do it now just to save a little time. So I get the target interface and place it right here. And now when I run this, at this point, this is using the code that I generated from this PWM generator. It's going to run it on the target. And I'll plot out what the PWM signal is here in blue, and red will be the model signal. Okay, so we see, again, these are slightly separated apart. But let me get this, hold on just for 1 second. I want to show this to you so you can actually see the effect of dimming. Okay, let me see. So we can do that. Where's the camera? Oh, what did I do? Okay. Let me get this up here so you can see it. Okay, so what I'm looking at is right there, that blue LED, right there. So take a look at that as I dim it and brighten it. So you should be able to see this thing dimming and brightening when I adjust this. Okay. So that's just a model to show how the dimming would work with this. What we want to do is we want to get to the point where you can actually use the hardware PWM on the 6.9M. That's very important because you're going to be using that then for motor control. But before I get there, we need a better way to transfer data, because transferring data at the 1 to 200 hertz over the JTAG is not fast enough. It's not going to show you enough detail, and you're going to see error between the model and the actual target processor. So what we have is we have a special high-speed interface that also works on the same JTAG connector between the host and the target. And what this does is it basically puts a buffer on the target, and it allows you to specify the buffer size. And that buffer will fill up at whatever the base frequency is of the target. So if you're running at 10 kilohertz, it's going to fill up at a 10 kilohertz frequency until it reaches this number of elements. In this case, I specified 1,001. And then it's going to flush the buffer out and restore another buffer. Every time the buffer fills up, it'll do a single transmit of the buffer over the JTAG up to the host. And that's where I'm reading it, and I'm plotting it out as kind of a burst of data into a plot, all 1,000 points at one time. So it's not exactly real-time data, but it's very close to giving you sections of real-time data that you can look at from the target. So again, this is called the monitor buffer feature, and it runs on the JTAG, and it allows you to collect data at the frequency that the target is running at and plot it out or record it on the host. So what we'll do is I'm going to do an example for you. And this is a sawtooth waveform. So what I have here, again, this is set up for the for a 6.9M board. This is the F28 config block. And if I go into the target calculations, first of all, I put a heartbeat on it. That's what this is up here. That way I know the board is running. And down here, this is the actual monitor buffer write. So this is the piece of the monitor buffer that resides on the target that's recording information. In this case, the information I'm recording, I made a sawtooth wave. I'm feeding it in, and what I'm doing here is I'm detecting when the sawtooth previous value, that's what this unit delay is greater than the current value. Well, if you think about the sawtooth, here's a picture of it right here. I'm pointing at it. That only occurs when you reach a falling edge of the sawtooth. So that trigger is occurring once per cycle when the sawtooth moves from its maximum value to its minimum value. It happens all at one time. So that's how this is triggering this buffer. And I have the buffer set to, in this case, 100 elements. So what I'm going to do, just to reiterate, this is a source model. I'm going to run it at 10 kilohertz. I'm running a sawtooth at 200 hertz, which means that it repeats every 0.005 seconds. And I'm going to record 100 points in this buffer. Each point is 0.1 milliseconds, so the total time history I'll get in the buffer will be 0.01 seconds. So in 0.01 seconds, I should see 2 cycles of the sawtooth, because one cycle takes 0.005 seconds. That's what I expect to see. So let's take the target calculations and create code for it. And I'm going to open the debug model. So the debug model is, all I have in the debug model is the target interface block. That's this block right here. And it's set up to run that out file that I generated from the source model. Now what's different here is I have one of these monitor buffer reads. These are paired blocks. One block goes on the target, that's the write block. One block goes on the host, that's the read block. So I've gathered the information off the target. Somehow I want to present it now on the host in this plot. So I'm using the analogous of the write, which is the read. You can tell which one is, you can have more than one of these. You can have as many as 16 you can have. And they're identified, they're paired together by their buffer ID number, it's called. So on the source model, this was buffer ID 0. And on the debug model, this is buffer ID 0. So it's reading the right buffer. Now, this is a little bit different than what you've seen before in terms of the plot. I've altered how the plot behaves. Normally the plot displays a time history value of a signal, but here what it's receiving is a vector of data, and that's this bold line, which consists of 100 points, and they're collected versus sample number. So there's no notion of time here anymore, it's just the sample number. And you recall that we're collecting it at 10 kilohertz or 0.0001 second intervals, and we're collecting 100 points. So that means that this range should be equal to 0.01 seconds or 10 milliseconds. So in order to configure the plot to interpret that data, I have to do a few things. First thing I have to do is hit the external trigger. That gives me that little dot. And that little dot is what controls the coordination between the write and the read data to the monitor buffer. Second thing that I have to do for readability is I need to scale the x-axis into the time range that I'm using. Because if I did nothing, it would just print out the sample number 0 to 100, which isn't really real helpful. I'd rather know what the seconds are. So I know that because of the calculation I just went through, this is going to be 10 milliseconds. So I've just set it 0 to 10 in milliseconds. I could make it 0 to 0.01 in seconds, I guess, if I wanted to say, like that. And now we can run this. Nope. I think I'm getting hosed up here. There's a problem. Just bear with me for 1 second. I'm going to have to power this thing off. I think when this happens, and I actually have been having trouble with my computer lately, you've got to actually close down the computer. I have to restart my computer when this happens. But let me go back to where we were. What we should have seen, and what we will see, is we'll see this plot right here. Let me just see if I can get this for you. Just bear with me for 1 second while I turn everything off.
Mm-hmm.
Oh, it's running. That's why. Okay. I think I found out what the problem was. Let me try this again. Okay. Yeah, the problem was I had another diagram running, and I hadn't turned it off. Let's see here. Okay, so what we're seeing here is exactly what I said. We're going to see 10 milliseconds. We're going to see 2 cycles. Just to show you that we can control this, let me go back to the source model. And what I'm going to do is increase the frequency. Okay, get rid of that. What I'm going to do is increase the frequency of the sawtooth from 2 to 400. That means that we should see 4 periods now instead of just the 2. So I'll regenerate code. And go back to the debug model. And yes, we see the 4 here. So this is a very accurate way to capture the data off the target interface. It's essential for doing any kind of work on the target interface. At the motor control level, you're going to need to have this kind of an accuracy to ensure the PWMs are working properly and that your sensors are working properly, and to be able to see it and plot it out. Okay. Let me just show you one more example on the oscilloscope display monitor buffer, and then I'll stop because I think I'm running a little bit over today. But this is, again, using the monitor buffer. And what I'm going to do here is try to sync on a sine wave and collect that information into the monitor buffer and plot it. So I have a source model. Again, there's a heartbeat going on the red LED. And I've got a monitor buffer into buffer ID number 1 with 200 points. And here I've just created a sine of omega t. And I'm cross-detecting when it goes from negative to positive. That's what this limit is doing. It's only allowing the positive pulse to come through. The cross-detect in solid thinking embed puts out either a +1 or a -1 value, depending on if you're going from minus to plus, it'll put a +1 out, or from plus to minus, it'll put a -1. I put the limit on so it would only detect the cross-detect going from minus to plus on a sine wave. So that's triggering the right block, and I'm recording 200 values. So we can create the code again for this, compile, and we can bring up the debug model. And this is the target interface block and the plot. So what I have here is I'm controlling the frequency now with this slider, but I'm syncing on the 200 points in the sine wave. So I can slow it. Let me slow it down a little bit so it's a little bit more viewable. Okay. So you see there's a little bit of latency there. I'm sending 200 points up, so it has to actually get the points and plot them out and flush the buffer out. But once it does that, you get a very good representation of that signal recorded at the frequency that I'm running the target at. Okay. So let me stop here. What I'm going to do is I'm going to zip up all the examples that were in this part of the presentation, and I'm going to send them to you so you have them, and you can run each one individually yourself. Actually, maybe I should do that after we finish Thursday, because I can send everything at one time then for you. I think that makes more sense. Let me do that. Okay. Well, I'm sorry I kept you later than I thought. It's like we're about 3:15.
It's all right. Yeah, question.
Yes.
Oh, the access to the video.
Rick.
Record. Are you able to send this video?
Oh, this video? Yes. Actually, yeah, I forgot I was recording it. Yeah. Stop